Another example of a alkyl halide, but we're going to see we have a dihalide here, and specifically we have potassium iodide. So it's a little bit of a different situation what we had before. We shouldn't expect just a basic substitution reaction to occur here, but we'll see what happens. So again, alkyl halide, the bromines are on adjacent carbons. We've got potassium iodide. No idea what the reaction is going to be, so let's go look it up. So when we go through our trusty resources, we can see eventually that if we've got a dihalide here, in this case two bromines on adjacent carbons, and we use potassium iodide, that a double bond is going to form in between the two substituents. So that's essentially what's going to happen. These are the byproducts. Remember in organic chemistry that a lot of times we don't show what the byproduct is. It isn't that we don't care. Yeah, sometimes it seems like we don't care. But here's the double bond. This is the majority product that's coming out of this, and that's the one that we're going to produce. So between the two bromines on these adjacent carbons here, we're going to produce a double bond on those carbons. So we'll redraw the molecule like this, and between these two carbons, that's where the bromines were located. We're just going to draw a double bond in between. In terms of naming, if I start from this side, I've got a 1, 2, 3. The double bond is in a 3 position. I'll have a methyl group in the 2 position up here, but the alkene is higher priority. So if I start from this side, 1, 2, the alkene gets a lower number. 3, 4 position is the methyl group, and this is the way that we're going to write this out. So I'm going to then, in the 4 position, I'm going to have a methyl group. And I'm going to have a 4-methylpentene. And I still need to say what carbon that pentene is on, so let's continue this through. So our 4-methyl, and I can say 2-pentene, or I can say 4-methyl pent 2-ene, like this. Now one thing to note, I have drawn in stereochemistry in here, but unfortunately in this reaction, we don't know specifically what the stereochemistry is going to be, so we're not going to do cis or trans or E or Z outside of this for the answer. So we're just going to denote that essentially this is it. If it was based on this stereochemistry that I've got set here, we've got the two H's, they're on opposite sides, they're not on the same side, as we say, so we would give this an E conformation. And then to denote the E conformation, then I would end up putting a bracket out front that says in the 2 position there is an E conformation on the 2-pentene. In this reaction we see an alkyl halide. In the 2 position here is the bromo, and we're reacting it with magnesium metal in ether, so we'll see it's a step 1, and then in a step 2 there's water. So we're going to take a look and see what these reagents will do. So knowing that this is generically the compound and it's an alkyl halide that's reacting, we're going to go and look this up. So when I look it up, I'll see that from this page here that if I have an alkyl halide and I react it with magnesium or lithium and water, essentially I'm going to replace the halogen with hydrogen. So I'm just going to create the alkanes from the alkyl halide. The example here is I've got a decyl bromide essentially, and so the bromine here gets replaced with a hydrogen. And so there's no more functionality here other than just it's a plain old alkane. I've lost that alkyl halide, it's completely gone by going through this process. So we're going to go through and do the same thing to our molecule. So I'm going to redraw the molecule like we always do. This is the carbon here that essentially we're dealing with, and I'm going to put a hydrogen on it. Boop, there's a hydrogen. So remember that we imply when we have the zigzag design that this is the carbon here is following the octet rule, and if I have a bond here with 2 electrons, a bond with two electrons here to this carbon and this carbon, that I must have 2 other atoms attached. They will be hydrogen, and I'll have 2 electrons in this bond, 2 electrons in this bond, and that fulfills the octet. So essentially then over here, this bromine, we actually had another hydrogen. We just don't have to show them all. And what we've done is replace this bromine with a hydrogen, and that is the reaction complete. So our final product then, if I erase these here, the final product then essentially is 1, 2, 3, 4. It's butane. And that's it. In this reaction, we've got an alcohol um, situated on a butane molecule. We're using concentrated sulfuric acid and heat. So let's go, it's a reaction of an alcohol. So let's go take a look at what this will produce. So if I were to scroll down the list here, this is close, but note that this is a base in heat. We are not dealing with a base. Also, this is using an alkyl halide. We're going to go down to and find an alcohol. There's one right there. And there's concentrated sulfuric acid or phosphoric acid and heat. And so the outcome then, this alcohol and the carbons adjacent to it are going to turn into a double bond. So this alcohol, the carbon here, and the carbon adjacent to that carbon, we're going to form a double bond there. So let's go take a look then at what we're going to form. So here we've got the alcohol situated here, and we've got two choices. We can either have the double bond get associated here or here. We're going to draw out those two possibilities. So the one I'm going to put here, and this is a second outcome that could happen. And so in the creation of the double bond, essentially, this is the preferred product overall. What happens is the double bond is situated between the two carbons that are more substituted, meaning if I were to take this carbon and count, I've got 1, 2, 3 carbons attached to this, so that's a tertiary carbon. And then if I count here, I've got 1, 2, so I've got a secondary carbon here. The double bond is situated between those. If I go over here, I'm going to have a secondary carbon and I'm going to have a primary carbon. So the preference for the double bond when it forms is between the most substituted carbons. This is the preferred product. So this is the one we're going to move forward with in naming. So for the naming, we're going to go through, I have a 1, 2, 3, 4. So I've got the alkene situated on a 2 position, and I have a methyl group situated on the 2 position. If I named from this side, 1, 2, the alkene's in the 2 position, but the methyl group's in the 3 position now. And so I got lower numbers if I start from this side. So I'm going to go from this side. So I've got a 2 methyl group. And in the 2 position then is the butene, or I can say 2 methyl. Oops, no butene. No space here. So one continuous word. So those are my two options for naming this compound. Note that there's no E or Z conformation here. If I go on this side in order to actually, I'll put the hydrogen here. So for naming for E and Z, I take a look at this carbon and I have to rate each of these carbons essentially and figure out which one is higher atomic number. And so if we look, I've got symmetry across both sides. So I've got a carbon with 3 hydrogens on this side, and I got a carbon with 3 hydrogens on this side. And because of that, there's no E or Z conformation that's associated with this molecule, so I don't have to write an E or Z in front. This example we see in alkyne again. Just note that this is a linear through the triple bond here, so this normally would be linear, but I've only drawn it just so I can showcase the number of carbons, that's all. So we've got 1, 2, 3, 4, 5 carbons. The triple bond's located here, and we're using this set of reagents. So again, if we don't know what we're doing and we don't have it memorized, we're going to go and look it up, which is the whole point of this exercise. So when I look through reactions or synthesis of alkenes in this case, if I have a starting point that is a triple bond and I use hydrogen, the palladium BaSO4 catalyst, and quinoline, I'm going to form the cis alkene. When we do it, we're going to form the cis, but we're going to name it in terms of E and Z. And then if I had the same triple bond, but I use a different set of reagents, I use sodium dissolved in ammonia liquid, then I'm going to get the trans conformation out of it. So we're going to get this. We're going to draw the cis confirmation, and then of course we're going to name it using IUPAC, E and Z. So to draw this now, I have to purposefully try to organize my carbons so that I can create a cis bond like this. So this would be cis, and if I had it drawn just straight through like this, this would be trans. This is not what we're looking for. Here we're looking for the cis conformation. So we count the carbons here, 1, 2, 3, 4, 5. So this is a pentane. In the 2 position is a pentene. So I can draw this and say that this is a 2-pentene, or I can say it's a pent-2-ene. But now I have to draw the confirmation. I have to state the conformation based off of the IUPAC E and Z naming. And so from this carbon here, I can say that this is higher atomic number than this one. And from this side here, on the ZAME side, I like using that for my students. ZAME meaning that it's a Z conformation 1 and 2. These carbons are on the ZAME side, so this is a Z conformation. If they were not on the ZAME side, it would be an E conformation. So to finish this off, I'm going to say that in the 2 position and the Z, there's a Z conformation in the 2 position here, and so there we go.